Chapter 11, the vapor and combined power cycles. Here are the objectives. I'm not going to run through each one. So we introduced the Carnot vapor cycle. 1 to 2 is isothermal, heat addition in a boiler. 2 to 3, isentropic expansion in a turbine. 3 to 4, isothermal heat rejection in a condenser. 4 to 1, back to 1 for a cycle. Isentropic compression in a compressor. And remember, the Carnot vapor cycle has no irreversibilities. The Carnot cycle is the most efficient cycle operating between two specified temperature limits, but is not a suitable model for power cycles because of these reasons for each one. Process 1 to 2, limiting the heat transfer process on two-phase systems severely limits the maximum temperature that can be used in a cycle. So when you are going around the cycle and you have 1, 2, 3, 4, and you're making this cycle. And remember, you have QH coming in and you have QL being exited. Sorry about that. I have gotten sick. So 1 to 2, there is a max temperature. And we know that because energy is transferred through heat and water, if we have a max temperature that we need to adhere to, then we are stunting our ability to transfer, so it's limiting. 2 to 3, the turbine cannot handle steam with a high moisture content because the impingement of liquid droplets on the turbine blades causing erosion and wear. So right here, we have degradation. Misspelled that. And then 4 to 1, it's not practical to design a compressor that handles two phases. So this is two-phase. But if all of those three, those three limitations considered and removed, actually, so those three removed, this is the most efficient cycle. The cycle in B is not suitable since it requires isentropic compression to extremely high pressures and isothermal heat transfer at variable pressures. So it's just saying, hey, we've designed this. Theoretically, it's the most perfect, right? The most efficient, but it's not feasible, and there are some limitations. Oh, sorry, I hope I don't cough after this. So here it is on a TS diagram, and so it's just talking about two vapor cycles in relation to entropy and temperature. So many of the impracticalities associated with the Carnot cycle that we just went through, the degradation, the max temperature, the two-phase, can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. And remember, we talked about that we can't, the simple answer to can we just remove the condenser, right, is a firm no. That's extremely important when you're making your way around this side, right? And you can see it in the blue tubing that you need it to be a lot cooler. The cycle that results in the Rankine cycle, which is the ideal cycle for vapor power plants. The ideal Rankine cycle does not involve any internal irreversibilities. So 1 to 2 is isentropic compression in a pump. You see it starts here instead of up here. So here, isentropic compression in a pump, and then constant pressure, 2 to 3, constant pressure and heat addition in a boiler. So the boiler is part of 2 to 3. And then 3 to 4 is isentropic expansion in a turbine. And then 4 to 1 is constant pressure heat rejection in a condenser. And this is a simple ideal Rankine cycle on the ATS diagram. And you can see 3 to 4 is in this superheated vapor section. The thermal efficient can be interpreted as a ratio of the area enclosed by the cycle on the TS diagram to the unit under the heat addition process. So it's just saying that the thermal efficiency is within the spot, right? Within it. It's enclosed. And here are the formulas of the steady flow energy equation. And this is when you are doing an energy analysis of the ideal Rankine cycle. And you do have individual equations, of course, for each device. So you have the pump, the boiler, the turbine, and the condenser. And then you have the network and the efficiency as well. The efficiency of power plants in the U.S. is often expressed in terms of heat rate, which is the amount of heat supplied in BTUs to generate 1 kilowatt of electricity. And here is that efficiency rating as well. The actual vapor power cycle differs from the ideal Rankine cycle as a result of irreversibilities in various components, of course. Right? If we have an ideal, then that means that we're going to actually have an actual version of that we experience with the irreversibilities, with the entropy. Fluid friction and heat loss to the surroundings are the two common sources of irreversibilities. Of course, because we can't escape that, right? We do have the isentropic efficiencies over here. And then just a little dot for A. So right here. Deviation of actual vapor power cycle from the ideal Rankine cycle. So you see that the solid line is our ideal. And you can see that, you should know that when you see entropy, the S, and this line right here going straight down because it's staying the same. But we know that this dotted line that really we're going to have an increase in entropy right here. So that should have clued you in. The effect, and then when we're talking about B, the effect of pump and turbine irreversibilities in the ideal Rankine cycle. And you can see that as well. See the change right here. And that's the presence of those irreversibilities. And right here too. You get a little bit right here. Most notable on that other side though. The basic idea behind all the modifications to increase thermal efficiency of a power cycle is the same. Increase the average temperature at which heat is transferred to the working fluid in a boiler. Why? Because our efficiency is going to get better. And what do we want to do? We want to decrease the average temperature at which heat is rejected from the working fluid. Why? Because it makes it more efficient, makes it more profitable. Lowering the condenser pressure. So you see lowers T low average. So to take advantage of the increased efficiencies at lower pressures, because remember we talked about, we can assume something is ideal when the temperature is negligible, right? Very low. Temperature change is very low. We also look at pressures. So to take advantage of the increased efficiencies at lower pressures, the condensers of steam power plants usually operate well below the atmospheric pressure. There is a lower limit to the pressure depending on the temperature of the cooling medium because temperature and pressure go hand in hand. There is a side effect. Lowering the condenser pressure increases the moisture content of the steam at the final stage of the turbine. And remember, we talked about that if you get something that has too much moisture, then we start getting into degradation of the device. And this is it here. You can see this where we started at. Right here, the first 4, and then when we moved, we got to 4 prime. And so this is what we did. We just decreased that temperature. And this is where we ended up with a new system. So, and then on the other hand, if you superheat the steam to high temperature, so you increase it, both the network and heat input increase as a result of superheating the steam to a higher temperature. overall effect is the increase in thermal efficiency since the average temperature at which heat is added increases. Of course, because you're having more heat, more energy to transfer. Superheating to higher temperature decreases the moisture content of the steam at the turbine, which is desirable, right? Because then we have less degradation. The temperature is limited by metallurgical considerations. Presently, the highest steam temperature allowed in the turbine inlet is about 620 degrees Celsius. Very high, but still limiting, right? This is still a limit. Okay? And so you can see here we started out at 4, and we're increasing the temperature. Started at 3, we're increasing the temperature to about right here, which in turn, while our temperature stays the same at 4, our entropy is increasing. And we're getting this increase in net work in the superheated region. Okay. So then what about if we increase the boiler pressure? So I hope you can see that we are going around each one, increasing to see what would happen. For a fixed turbine inlet temperature, the cycle shifts to the left, and the moisture content of the steam in the turbine exit increases. The side effect can be corrected by reheating the system. So it is I won't say fixable, but maybe able to be offsetted. So you can see the temperature increase, and you can see the entropy drop or reduction, right? And then how this is worked. Sorry. And one thing that I want to note is everything under this curve, right, is a two-phase mixture. So before, where we had the increase in the superheated vapor region, it was burning off all of that liquid. But here we're actually increasing because the majority of what's being increased is under the area of the dome. So we're increasing that moisture content. Today, many modern steam power plants operate at supercritical pressures, so pressures that are in excess of 22.06 megapascals, and have thermal efficiencies of about 40% for fossil fuel plants and 34% for nuclear plants. And so this is showing you see this critical point, and then they are operating above. So when you are north of this critical point, this is supercritical. I like that terminology. So how can we take advantage of the increased efficiencies at higher boiler pressures without facing the problems of excess moisture at the final stages of the turbine? Because that's what we want to reduce. So one, we can superheat the steam to very high temperatures, and it is limited. And then you can expand the steam in the turbine in 2 stages and reheat it in between. So remember, we went over that. We went over where we, I believe it was a pressure. We compressed it, and then we cooled it, and then we compressed it again. And so we had 2 different stages. You can see that here, right? So we're going up, we have a high pressure turbine, and then we're going to reheat it again so that we have, instead of just coming down here, right, we need it out from this 2-phase mixture. So we need to move it over. So we're going to reheat it to bring it back up so that it can fall here and have just a little bit catching in this mixture instead of all of this. Right, so that's what we would gain there. Okay, so here's the formulas for these in the ideal Rankine cycle. And then here, you see we've added in a reheater, and it goes back into the boiler that we already have in the system. So here we have the high pressure turbine, and then we go, let's follow it around from 1. So 1, we're going from the condenser to the pump. And then from the pump, we're going to heat it in the boiler. And then we're going to go around to a high pressure turbine. Let me erase these off so that you can see it here, what we've done so far. Okay. So from 1 to 2, we've gone into a pump and we've increased the temperature just a little bit, not a whole lot, but just a little bit. But then 2 to 3, we are increasing the temperature a ton, right? Because we went to the boiler. 2 to 3, we went through the boiler. And then 3 to 4, we're cooling down, coming out of that high pressure turbine. And then we're going back into the boiler from 4 to 5. So we're heated back up. Now we're at 5, we're going from 5 to 6, and we are cooling down. And then 6 to 1, sorry, we're going back through the condenser. Right here. So that's the way that we're making it around. And remember, we are going to follow these, and you can add them. You can add even another reheater and bring it even further out into the superheated vapor region. Not necessary, but you could, picture how that would look. The single reheat is a modern power plant. In a modern power plant, improves the cycle efficiency by 4 to 5% by increasing the average temperature at which the heat is transferred to the steam. Okay? And then the average temperature during a reheat process can be increased by increasing the number of expansion or reheat stages. That's what I just mentioned. As the number of stages increase, the expansion and reheat processes approach an isothermal or constant temperature process at the maximum temperature. So remember, we still have those maximum limitations, right? However, the use of more than 2 reheat stages is not practical. The theoretical improvement in efficiency from the second reheat is about half of which of just a single reheat. So as you add reheating, the efficiency or a theoretical improvement in efficiency is not linear. So it definitely diminishes on a return drastically. The reheat temperatures are very close or equal to the turbine inlet pressure, and the optimum reheat pressure is about 1/4 of the maximum cycle pressure. And so it just goes in here, and it's just showing you that while you go, up and down, you do have just an average reheat. There's an optimum reheat pressure in the reheat ranking cycle for which the thermal efficiency is maximum, and this is it just plotted for efficiency over reheat pressure. So here, the first part of the heat addition process in a boiler takes place at a relatively low temperature. So remember, we started off over here very, very low, right? So heat is transferred to the working fluid during processes 2 to 2, and this is when we're doing a low temperature heat addition. So we're going 1 to 2, and then we've added some low temperature heat additions. So 2 to 2 prime, because that's our addition. Okay, and then in steam power plants, steam is extracted from the turbine at various points, of course, because we want to reduce the moisture buildup. This steam, which could have produced more work by expanded further in the turbine, is used to heat the feed water instead. So remember a couple of lectures ago we were talking about, well, maybe we can just power this shaft by using, like robbing some power over here. That's what it's doing. So it's saying, hey, it does produce work, but we just can't have it here. Well, let's use it to heat the feed water instead. And this device, where the feed water is heated by the regeneration, is called the regenerator or a feed water heater. And you'll see that a lot. Feed water heater. Feed water heater is basically a heat exchanger where the heat is transferred from the steam to the feed water either by mixing the two fluid streams. So an open feed water where you just have, like maybe 2 inlets, right, and 1 exit. And so you have the 2 mixing, or a closed water, which you can look at it like our tube. I mean, they have other designs too, but you can have A and B mixtures. So you can either directly mix it or indirectly mix it, depending on what your needs are. And here it is, right here. Here's an open feed water heater, just like that. So you have mixture A and mixture B, and it's coming out AB. So an open or direct contact, that's because the fluids are mixing together directly. Feed water heater is basically a mixing chamber where the steam extracted from the turbine, so you see the steam right here, A is the steam, extracted from the turbine mixes with the feed water exiting the pump. So you hear the pump. I'm going to do feed. Let's see if I can write sideways without pressing buttons, apparently. No, I guess that's a feed water. Okay. Ideally, the mixture leaves the heater as a saturated liquid at the heater pressure. And so then it leaves here at saturated. Ideally, right? And then here's those formulas to associate with those. And then you can see it here on a TS diagram as well. So closed feed water heater, here it looks a lot like an open, but you can see that this feed water right here is going in and it's going through the tubing right here, and it's coming out of here. And then the steam is coming in and it's heating everything around it, and then it's exiting. And you need an additional pump for that. Another type of feed water heater frequently used in steam power plants is the closed feed water heater, in which heat is transferred from the extracted steam to the feed water without any physical mixing or direct contact taking place. The 2 steams now can be at different pressures since they do not mix. All right, so if you need to keep them at different pressures, you can do that. Closed feed water heaters are more complex, of course, because of the internal tubing network, and thus they are more expensive. Heat transfer in closed feed water heaters is less effective since the 2 streams are not allowed to be in direct contact because you lose some of that in that barrier, which is this tubing. However, closed feed water heaters do not require a separate pump for each heater, since the extracted steam and the feed water can be at different pressures. So you don't need each one to address the pressure situations of the 2 mixers. Open feed water heaters are simple and inexpensive and have good heat transfer characteristics because they can directly mix. For each heater, however, a pump is required to handle the feed water, and that's to address the pressures. Most steam power plants use a combination of open and closed feed water heaters because the designs of each one are different, and even if they have power plants with multiple of these situations, not each one may be identical. Here's exergy destruction. We didn't really go over this in detail, and so I also won't go through this in too much detail. The cogeneration. So many industries require energy input in the form of heat, and that's called the process heat. Okay. Process heat. And it's the energy input in the form of heat. So process heat in these industries is usually supplied by steam at a 5 to 7 atmosphere and 150 to 200 degrees Celsius. Energy is usually transferred to the steam by burning coal, oil, natural gas, or another fuel in a furnace. Okay. Industries use large amounts of process heat, also consume a large amount of electrical power because you need to heat it. So you're going to have a large amount of electrical power to use large amounts of heat or to process that. It makes sense to use the already existing work potential to produce power instead of letting it go to waste. And so that's taking that heat transfer out and reusing it. The result is the plant that produces electricity while meeting the process heating requires of a certain industry. So cogeneration is the production of more than one useful form of energy, such as process heat and electrical power, for the same energy source. For example, if you've ever been to Disney World, they have in Epcot, they have a ride. I cannot remember the name, but I guess that doesn't really matter. But it's one where you are on this little boat and it takes you through a greenhouse, and it's on the water. You can see the vegetation and everything like that. Anyway, so they use everything within it. So the food that they grow, that is lab grown, or I guess you could call it a lab, that is lab grown, is used in their restaurants. The energy that is that they are able to capture from the running water for the ride and things like that, it goes to power some of Disney. And everything about this ride is, hey, we take everything and put it back into it. And what it is they're generating more than what they're using. So they're generating more power on the ride, or generating more than what they need to make the ride function. So they take that, and instead of just letting it go to waste, they're using it. A lot of power plants do this with putting power into the grid, and residential homes can do that as well. So if you have solar powers on your roof and you're capturing way more power than is necessary to power your home, you can sell that power back to the power company. And that's cogeneration on a very small basis. Or a power plant will produce so much energy, they will convert it to residential areas and things like that. And you will sometimes find that the wattage rate to power your own home is a little bit cheaper when you are around a power plant, just because you're getting energy byproduct from it. So here's the utilization factor here. So this E is factor, and that's utilization. The utilization factor of an ideal steam turbine cogeneration plant is 100%, of course, because it's ideal. So of course we want it to 100%. But actual cogeneration plants have a utilization factor as high as 80%. That's fantastic. That's a great utilization factor. Some recent cogeneration plants have even higher utilization factors, and I'm sure that has come at a hefty expense as well. So here's adjustable loads. At times of high demand for process heat, all the steam is routed to the process heating units and none to the condenser. The waste heat is 0 in this mode, and that's because we're diverting all of it. If it is not sufficient, some steam leaving the boiler is throttled by an expansion or pressure reducing valve to the extraction pressure, P6, and is directed to the process heating unit. So what we're saying is that we have all of these like shortcuts, right? So we can do P6 here. We can divert some. We can divert some here to this process heater. We can take a little more if that's what we need. Maximum process heating is realized when all the steam leaving the boiler, right here, all the steam leaving the boiler passes through the valve and no power is produced in this mode. When there's no demand for process heat, all the steam passes through the turbine. So this would be turned off, and when there's no demand, then it would all go into the turbine. And the cogeneration plant operates as an ordinary steam power plant. So what this is going on to tell you is, of course, the continued quest for higher thermal efficiencies has resulted in a rather innovative modifications to conventional power plants. That's because we want it to be more profitable. We want it to be more efficient. So higher thermal efficiencies has caused innovative modifications. Hey, can we add a pump here? Hey, can we take this, waste, this heat waste, and plug it in over here? Can we reheat the system to get it out of that or into the superheated vapor? Any kind of stretch into something, maybe an efficiency or a bottom line, things like that, pushes innovative modifications. A popular modification involves gas power cycles topping a vapor power cycle, which is called the combined gas vapor cycle, or just the combined cycle. So what we're doing is we're taking the existing devices or new devices, but mostly the existing devices, and moving them around and placing them together and just seeing what would happen and seeing if it addresses something that can be improved, right? And that's why we've been getting so much into efficiency, because that's where we can look at where we need to improve, and we measure that as opposed to the ideal versions of themselves to see how close we're getting. The combined cycle of greatest interest is the gas turbine, the Brayton cycle, topping a steam turbine or Rankine cycle. So the combined cycle of greatest interest, because you can have multiple, right? You can combine multiple different ones. But the biggest one is the Brayton cycle topping a Rankine cycle, which has a higher thermal efficiency than either of the cycles executed individually. So those two together do produce a higher thermal efficiency than either of the two separately, which is not always the case, right? It makes engineering sense to take advantage of very desirable characteristics of the gas turbine cycle at high temperatures, and also to use the high temperature exhaust gases at the energy source of the bottoming cycle, such as a steam power cycle. The result is the combined gas steam cycle. Okay. The recent developments in gas turbine technology have made the combined gas steam cycle economically and very, very attractive. So that means that it's affordable. The combined cycle increases the efficiency without increasing the initial cost greatly. This is fantastic. So increases the efficiency with only, little bit increase in the initial cost. Because of this, many new power plants operate on combined cycles, and many more existing steam or gas turbine plants are being converted. And that's nice. So if you can make it, of course, the cost of it is going to be less if you're building it from scratch, because you can just build to those modifications. But it's really nice if you have something that you can convert. And so then you can capitalize on that increased efficiency. And here you go, you see it, right? So it is the Brayton cycle topping the Rankine cycle. Okay. And so you hear Rankine and then Brayton. So if you were picturing it physically on top, you were right. So here's the steam cycle and the gas cycle. And you see that it shares this heat exchanger right here. This is where it joins. And you can see, you can put them both on a TS diagram. And so here you have the gas cycle, you have QN going in, and then you have the steam cycle. So just some information. So this 1090 MW Tohoku combined power plant that was put commercial operation in 1985 in Japan is reported to operate at thermal efficiency of 44%. This plant has two 191 MW steam turbines and six 118 MW gas turbines. Hot combustion gases enter the gas turbines at 1154 degrees Celsius. That is hot. And steam enters the steam turbines at 500 degrees Celsius. The steam is cooled in the condenser by cooling the water at an average temperature of 15 degrees Celsius. The compressors have a pressure ratio of 14, and the mass flow rate of the air of the compressor is 443 kilograms per second. That's huge. A 1350 MW combined cycle power plant built And in Barley, Turkey, in 1988 by Siemens, is the first commercially operating thermal plant in the world to attain efficiency levels as high as 52.5. So significant versus 44%. But when you're talking about it in comparison to the ideal version, 100%, it's half, right? Well, close to half. This plant has 6 150 MW gas turbines and 3 173 MW turbines. Another plant built by Siemens. So, does this one say who this one was built? Or maybe this. Yeah, it doesn't have it, but it looks like Siemens is doing a great job increasing. So, in Germany, reached a thermal efficiency of 60.8 in electrical output. This is wild. So, in this time, what is that, 12, 23 years? In 23 years, they increased it about 8%. And that's significant. But isn't it wild when you look at it on a math level? 2016, GE reported 62%, and the new target for thermal efficiency is 65%, which is approaching the Carnot limit, because remember we have those heat limits, right? So just summary, we kind of went through all of those, but really to just talk about, we talked about the Carnot vapor cycle, the Rankine cycle, which is the ideal cycle for vapor power cycles, the deviation of actual, of course, because when you have irreversibilities, which we do, it's going to obviously deviate from an idealized. How can we increase the efficiency of a Rankine cycle? Well, we talked a lot about that. We were talking about reheat, right? Reheat, regenerative Rankine cycle. Second law analysis of the vapor power cycles, that'll be covered when you're actually starting to work it. Cogeneration, we talked about that. If you have waste and you can use it, use it. And then combined gas vapor cycles, and that's when you have the gas atop the steam cycle, right? And it's joined by that heater.